So rotational inertia is one of the most important concepts in rotation, rotational dynamics, angular momentum, and so forth. It comes up a lot. And rotational inertia is resistance of an object to changes in rotation due to the distribution of mass relative to an axis of rotation. That's pretty wordy. Basically what it boils down to, if I have some sort of object, some sort of physical object, say like this rod, that this has some sort of fixed mass m. If I were to drop it, then it would gain momentum, okay? But whether it's moving or not, it's going to have some sort of inertia that's going to cause a resistance to its change. So that depending on what force is being applied, it's going to get a different acceleration depending on the force. So that if I wanted to change the behavior of this, I would have to apply a force, I get an acceleration, and that was Newton's second law. So this mass here is inertia. So when we look at Newton's second law for rotation, our rotational inertia came in a very similar format. There's basically similar relationship between force and torque as there is linear acceleration and angular acceleration. So there is going to be a relationship here with rotational inertia. Rotational inertia is also sometimes called the moment of inertia, and actually I tend to use moment of inertia more often because it shows up a lot more in like the Physics C texts, which I'm more familiar with. So they're used interchangeably, so I'm going to kind of go back and forth between them, but moment of inertia and rotational inertia are essentially the same thing. Let's break down this definition a little bit more. So it's resistive of an object to changes in rotation. So that's the whole idea that if I apply a torque to try and change the rotation, the bigger my moment of inertia, the smaller the angular acceleration I'm going to get. And it's based on the distribution of mass relative to an axis. So if I were to say have like a rod, that same rod here over here, and it's got a mass. If I were to try and rotate it, say about its center, then its rotational inertia is dependent not just on its mass, but where the mass is located relative to the axis. So the fact that some of the mass is over here, some of the mass is in the center, some of the mass is over here is going to make a difference. Because if I try and take that same rod and rotate it about an end over here, like I was trying to swing it like a bat, so this is like doing that, this would be like doing this, that I'm going to have the same mass in both cases, but when I look at how far my mass is from my axis of rotation, I can see that this mass over here is very, very far away from my axis of rotation. Now, the formulas for rotational inertia are going to look something kind of like this, where this beta is not really a variable, it's just a placeholder. It's a proportionality constant. So that basically if I were to figure out, if I know the mass and I know the physical dimensions, that there is some sort of factor that is going to modify what the actual rotation is. This factor is based on the shape of the object and the location of the axis relative to it, so that even though these have the same mass, because their mass is distributed differently about the axis in these two cases, they're going to have a different coefficient here, different value for beta. And it's also going to matter if the objects are uniform or not. The objects we're going to look at are generally going to be uniform objects. That means constant density. So if I have this rod that has a constant density, so that all of the mass is equally divided up between the lengths, whereas if I had a rod that say was like less dense on one end, but then was maybe more dense on the other, because maybe you stuffed something inside of it, or it's a compressed material, that even if you rotate these same objects and they have the exact same mass, they have the exact same length, that because their mass is distributed differently about even the same axis, these two are not going to have the same constant here. And most of this is going to be devoted to telling you, like, how does that constant vary. But one thing that's going to be true about that constant is always going to be somewhere between 0 and 1. That basically the maximum moment of inertia you could have is going to be mr squared. So the mass times the radius squared is going to be your maximum value possible for an object. Not all objects will be able to have that same moment of inertia. So the units of moment of inertia basically are going to be kilogram meter squared, because you're taking a mass times a length unit and you're squaring it. So it's a scalar value. It is not a vector. It does not have its own direction associated with it. So what we're going to do is we're going to take a look at the rotational inertias of common objects, starting with a point mass. Then we're going to talk about how do you find the moment inertia for other objects. So for example, I'm going to teach you like a formula for a hoop, and then I'm going to teach you a formula for a rod. So if I wanted to say make a bicycle wheel, I could have a hoop, and then I could have some rods, and I now have a bicycle wheel. So the rotational inertia can be the sum of a bunch of these simpler objects. What we're not going to do is we're not going to look at objects that are particularly irregular. Everything you're going to do in Physics 1, you're going to be able to essentially approximate as one of the simple objects, or a combination of those simple objects. Or the only reason they might not, if they did give you some weird wibbly wobbly blob, is that if you use Newton's second law for rotation, if I know what torque is being applied and I can measure the angular acceleration, I can find my rotational inertia for this unknown object using this information. So if you can use this one, awesome. But if you can't, then usually it's because you can use dynamics to find it using a different method. And that's actually what your lab next week is going to be over. Is you're going to be given a different object that's not standard shape, and you're going to apply known torques, measure angular accelerations, or calculate, and then be able to determine the rotational inertia. All right, so what I'm going to do is I'm going to talk about the rotational inertia of regularly shaped objects. So a couple of things about these formulas. The first thing is they only apply to uniform objects. Uniform means they have to have the same density throughout. At least according to their shape. So obviously, like a hollow sphere is not going to have the same density throughout, but basically it's going to have the same density throughout its surface area, and the center would be hollow. But something like a ping pong ball would be like a hollow sphere. A solid sphere would be something approximated by like a solid like ball bearing. But something that would not really fit these definitions would be something like a golf ball, which is made up of a whole bunch of different materials that have different densities. So they have to be kind of uniform. They have to be essentially made with the same density, the same material, and so forth. Let's start with the point mass. We kind of already talked about a point mass the other day. We basically said that if I have a point mass here which has a mass of m, and it's located some radius of r from an axis of rotation, that if I were to apply a force to that point mass, that force would be exerting a torque. The torque would be equal to r times f. And then if that's the only force acting, then that force is also going to be the net force. So we said the torque is going to be r times f, and f would be m times a. And then that linear acceleration is essentially related to the angular acceleration, because that linear acceleration would actually be tangent to the circle, and your tangential acceleration is r times alpha. So if you substitute in r alpha for a, you get that torque is going to be r times m times r alpha, and then if you rearrange this, you get torque is equal to mr squared times alpha. So this is the moment of inertia of a point mass. So if, say, I had 2 point masses here, and I had one has a mass of m and the other has like a mass of big M. And the idea is that I can choose anywhere to be my axis of rotation. So for example, if I wanted to choose this point out here to be my axis of rotation, let's just call this M1. and this one M2, then this could be R1, and that could be R2, and then I could add up their moment of inertia, treating them as point masses. So the total moment of inertia would basically be the sum of all of the little individual moments of inertia for each of those. So in this case, that would be M1 R1 squared plus M2 R2 squared. And I could sum that up and go. Realizing that if I picked a different axis of rotation, for example, if instead of going about this arbitrary point here, if I wanted to rotate this system, say about this point mass, then that moment of inertia would be based on, say, this other, this would now be R2, so these wouldn't exist. So that would now be the separation distance, and then this one would have no moment of inertia, and this one would have moment of inertia, so that would be just M2 R2 squared. So even though there's two different point masses, because my axis of rotation goes through that one, its lever arm, its R is 0, so therefore it's not contributing to the moment of inertia. So, but I can always do that. So the collection of point masses basically just says, find an axis of rotation, determine the moment of inertia of each point relative to that axis, and add them up. Now, the thin hoop, so if I look at the hoop from like a top-down view, I'm talking about like an axis of rotation that goes through the center here. So if this hoop has a mass of m, and it has a radius of r, one thing I'm assuming is the axis of rotation is going straight through the center. In this picture over here, I've kind of rotated on its side, so you can kind of see that the axis of rotation would be here, and then this would be kind of in the plane of the page. So the moment inertia for this one is really kind of interesting, because if I were to treat this as a collection of little tiny point masses, if this is my little mi ri squared, and then I have a little mi ri squared for this one, and a little mi on and on and on, one thing that's true is all of these r's are actually at a radius of r. So when I take my moment of inertia to be the sum of little mi r squared, basically the r squared is the same for all of them. And so in this little sum of here, this is my total mass for that. So this is just mr squared. So the hoop has the exact same formula as a point mass. It's just this m is going to be the total mass of the object, because all of the mass is located at a radius of r from the axis of rotation. So your hoop is going to have a really large moment of inertia. That's part of the reason why bicycle wheels are essentially hoops. Because if you want to stay rotating and not fall over, to be more stable and get the kind of gyroscopic effect that you get with like a motorcycle or a bicycle, you want to have kind of that larger moment of inertia, so that you're going to keep on rotating, keep on doing what you're doing. So the next ones are solid disk. So here I'm doing a side view kind of. You could look at a top-down view. It would just be a circle there. The idea is that this whole thing has a mass of m. Now, if I were to think of this as a collection of point masses, so this would have a little mi ri squared here, but this point right here would be an mi ri squared, but the r's are different for these two. So some of the mass is still located at a radius of r, but others of the mass are located closer, and like the mass dead at the center, there's no moment of inertia for that because it's at the axis of rotation. So we can't have the same moment of inertia that we had here, assuming this was the same mass m, the same radius r, same total mass, made out of like a different material or something. Then it's going to have to be smaller. And actually what's really cool with a solid disk is if it's uniform, it's the same density throughout. What happens is your moment of inertia is exactly half of the rotational inertia that you would have of a hoop with the exact same mass and exact same radius. So the next shape are going to be the rods. So it's a long, thin rod. So by describing it as a long, thin rod, we're essentially assuming that the thickness doesn't matter. So I could consider this rod to be a collection of point masses. Okay, so this is just a collection of point masses. So where I rotate this rod matters. So for example, if I were to hold it on this end, if I look at, say, like this little point mass here, this is going to have its little mi ri squared. But if I look at this point mass way over here, it's going to have an mi/ri squared. And because this is going to be a very large r, actually its r is going to be the length L, that is going to be very far away, and you've got a square here. The fact that you have all of this mass located really far away is going to cause a large moment of inertia, or at least a larger moment of inertia. But some of your mass is still located at or really close to the axis of rotation, so it's again going to be smaller than a hoop. So in this case, the moment of inertia of a long thin rod is going to be 1/3 ml squared. So once again, now we're going to length L. It's still kind of acting like a lever arm, it's still acting like R, but we're calling it L because it makes more sense for it to be a length rather than a radius when you think of the physical construction of the object. So that would be a long thin rod. So that would be something going like an axis like this. The axis right here is in the page, so I'd have to rotate this like this. So rotating my rod, like holding it and spinning it in circles, like that's what we're talking about here. If I roll the rod like this, that's actually acting like a disc. So the thickness of this disc doesn't matter. It doesn't have to be a thin disc, it's just a solid disc. So because this is being rotated about its center, if I spin it like this, it's rotating about its center, which is the same thing we have here. So this is an end kind of in and out of the page, kind of like I was doing something like that. And then the next one is about the center. So if I were instead to look at the long thin rod and spin about the center, that's doing this. So if I'm rotating it about its center here, and I don't know if you can tell, but it's a lot easier for me to do this than it is to do that. And that's because when I look at my mass distribution, I'm going to have some of my mass still located here at the axis of rotation. But then when I look, I'm going to have mass here and mass here. But the furthest lever arm I ever get is L/2. So I'm going to have more of my mass concentrated towards the center. So my moment of inertia is going to be actually a lot smaller. And the moment of inertia of a long thin rod about the center is 1/12 ml squared. One thing that's special about the center is where the center of mass is. So if you make your axis of rotation the center of mass on an object, that will always give you the lowest moment of inertia possible. So if this was a non-uniform rod, so maybe it was like a baseball bat, softball bat, oh, that's a really bad bat. Okay, something like that. The center of mass of this is not going to be in the center of the object. So say the center of mass is right here. So if I wanted to have this bat have the lowest moment of inertia possible, I could hold it here, and that would give me the lowest moment of inertia. When we actually hold the bats at the end, way over here, you have a huge amount of mass located a very long distance away from your axis of rotation. This is actually going to cause a very high moment of inertia. You have to put a lot of force and energy into rotating that object. But once you get it rotating, it's going to keep on rotating, and it's also going to cause nice transfers of momentum when you have collisions. So that's why we're going to do that. But if you want that bat to swing faster, you need to choke up on the bat, because you're going to need to decrease the rotational inertia so you can get that bat moving faster and get a quicker turn on it. So we are assuming we are rotating them about an axis through the center. So this is what it would be if you were rolling the ball around somewhere. It's gonna rotate about an axis kind of through its midpoint. So if you compare this to like a hoop that has the same radius, the thing about the hoop is all of the mass is located at a radius of r. You're gonna have, like a hollow sphere, a lot of your mass located at a radius r, but because the axis is actually physically cutting through the sphere, you're going to end up with some of the mass in contact with the axis of rotation on the top and bottom. And for a solid sphere, you're also going to have some of your mass in contact all the way throughout. So what's going to end up happening is your spheres are going to have a lower rotational inertia than your hoop, and then the hollow sphere is going to be higher than the solid sphere, because the hollow sphere is going to have more mass located on the outside, whereas your solid sphere is going to have more mass located on the inside relative to each other. So I always have a hard time remembering these ones off the top of my head as which is which right away. The fractions are 2/5 and 2/3. So since the 2/3 is a larger fraction, that means this is the one that's going to belong to the one that has higher rotational inertia. The hollow sphere is going to have higher rotational inertia, so it's going to be 2/3 mr squared. and the solid sphere is going to be 2/5 mr squared. So like I said, these are formulas that you want to memorize. These are good to have in your head. They're not on the formula sheet, but having them memorized is not enough. The discussions that I've just gone through about where the mass is located, and that's the key term, is mass distribution. Anytime you are qualitatively trying to explain why one object has more rotational inertia than another, it's about where is the mass distributed relative to the axis of rotation. So that's relative to the axis of rotation. So that's going to be your key. Now we're going to take a look at two other examples of different ways you can calculate rotational inertia for some special cases. So here's my axis of rotation. If this is the length here of my hammer, and maybe this guy has a mass of m, and the handle has a mass of m, then if I wanted to find the moment of inertia of the hammer, what I could do is I can do I for a rod about the end plus I for a point mass. This process right here is called the perpendicular axis theorem. The perpendicular axis theorem says basically, hey, if I want to find and if I have an axis here and these objects are all essentially along a line that's perpendicular to my axis, which it is, my axis is not on the page, so these objects are all perpendicular to that axis, then I can just add them up. So if I wanted to find I of this hammer, well, I of the rod about the end is going to be the 1/3 ml squared. And then if I'm treating this mass as a point mass, because they didn't necessarily give me a thickness here to be doing anything with, I'm treating that as a point mass. That point mass is going to be mr squared. So that would be mr. R is going to be L, so it's going to be ml squared. So then I can find my moment of inertia by combining fractions. So I could do 3/3. So I can find that I of my hammer is equal to 4/3 ml squared. So that's the perpendicular axis theorem. The other theorem that you might have to use is the parallel axis theorem. And this one's kind of cool. And you'll do more of this in Physics C, but I wanted to introduce it to you just in case it comes up. The parallel axis theorem says that if you know the moment of inertia about some point, about the center of mass, that if you add some other md squared, so if you move that axis of rotation to a distance d, that you can find a new moment of inertia about any point. So this is really relevant for things like the rods, or like I talked about, if you take a hoop and instead of rotating it about the center, you want to rotate it about an axis over here. So if this is the center of mass here and this is the distance d, if I want to rotate it about this axis of rotation, that would be like point P. So if I wanted to find the moment inertia of this hoop about point P, well, the moment inertia about point P is going to equal the mass of the hoop times that distance d. Well, that distance d in this case, if this has a radius of r, well, that's going to be mr squared, plus the moment inertia of the hoop about the center of mass is going to be mr squared. So I'm going to get the moment inertia about point P is going to be 2mr squared. So I'm essentially going to double the moment of inertia of this hoop by rotating about a point on the edge and rotating it at, you know, kind of like this around that point, rather than rotating it about its center. And we can check that out here. So if in a different example, I wanted to say, look at these rods. If I had a long, thin rod here, its center of mass would be here at the center. So if I had a length here and a mass, if I wanted point P to be this point at the end, I could say that the moment inertia at point P is going to be I about the center of mass plus md squared. Well, I of the center of mass is going to be the rod about its center, which is going to be 1/12 ml squared, plus md squared, well, d would be this distance here. Well, that's going to be L over 2. And we get 1/12 ml squared plus 1/4 ml squared. And then if I do multiply this by 3 over 3, so it's going to give me 3/12. That's going to give me 4/12 ml squared, which is the same thing as 1/3 ml squared. So you can find and prove that the long thin rod about the center and the end are related, but that would also allow you, if point P was say here, and this was D, and D was L over 4, I could then find the moment of inertia for any point along this rod, assuming that it's uniform. Okay, if this thing was denser on one end than on the other, then that would be a different story. But that gives you some ideas for how to calculate moment of inertia for different objects. So you're going to get a chance to practice applying this before we start going full on into kind of calculation-based problems.